morning, students. In the previous lectures, we have seen how to design vertical retaining walls, and now let us look at how to design the embankments or slopes. Well, what are the design approaches, and especially when it comes to definition, what is an embankment and what is a wall? Slopes that are steeper than 70 degrees are designed as retaining walls, and the slopes that are shallower than 70 degrees are designed as slopes, and we will see some of the principles applicable for these for the design of slopes in the lectures to follow. Here is an example of an extreme case of a slope. It is the airport that is being constructed at Sikkim. This is the view, this is the schematic view of the airport runway, and this being a hilly terrain, there is no flat ground and we need to make up a ground, and in order to make up, engineers had to build up this slope all around these dotted lines all around, and the cross section you can see here, the height is about nearly 110 meters. It is it's a very steep faced embankment, as you can see, and it is one of the most challenging projects that has ever been taken up in India, and this work is being carried out by McAfee India. Well, whenever we have an embankment or a slope, as you can see on the roadsides or railway embankments, the surface is free to the rainwater or wind erosion and so on. And how do we protect the surface on the slopes? There are different methods. The best method is by far growing the vegetation, and we can use erosion control mats like coir mat, jute or crimped mesh and so on, or we can use stone pitching, but the effectiveness of the stone pitching is doubtful, especially when your face is very steep. The stones may start falling down or just simply creeping down because of several reasons, or we can use a spray concrete on the surface, or we can give gabion facings and so on. Here is an example on the face treatment using a combination of geocells that we have seen earlier, and then the vegetation that is growing through the pockets of these geocells. And here is an example of a crimped mesh and a polymeric textile that can be used to protect the surface of the slopes. And these are different examples of coir and jute that can be used for controlling erosion on the slopes. The rainwater induced erosion usually results in gully formation like this that we frequently see on the Indian roads and embankments, and once it is treated with coir or jute cover, and if we can promote the vegetation, the surface looks something like this. Is actually in the inset you can see the coir mat that is exposed, and by far the growth of vegetation is the best solution for controlling the erosion on the slopes. And here we see an example of using spray concrete, and sometimes the spray concrete may not stay on the surface, on the slope surface, especially if the slope is very steep. In such cases, we use the geocells, which are the three-dimensional form of geosynthetics that we have seen earlier. We can spread them and then fill these pockets with cement concrete, so that we provide a good erosion control on the surface. And this particular photograph shows the erosion control within a canal slope. And what do we do with existing slopes? We have many slopes that are existing already constructed, but which show signs of distress, and we can use different techniques like the soil nails. Actually, a nail is nothing but a steel rod that we drive into the slope to connect the active part, that is the moving part of the slope, with the passive part, that is the resisting part of the slope. And here we can see the nails being driven, or we can use a grouted anchor. Actually, we drill a hole and then fill them with cement concrete. It could be quick setting type. Then we can also use pre-stressed anchors. Actually, here you see an example of the pre-stressing of an anchor. We install an anchor and then we pre-stress it, so that the inside soil is in compression, and we know that if the soil is kept in compression, it behaves like a very strong and stiff material. And what are the requirements of the soils for the construction of embankments or the slopes? The requirements are a bit less stringent as compared to the vertical retaining walls, mainly because these embankments or the slopes, they can tolerate larger deformations, because they are spread over a very large area. The gradation is given here, but one thing that we need to see is we can have about 50% of the fines passing through 75 micron sieve. In the previous case for the retaining walls, we have seen that this percentage is not more than about 10 to 15%, and then the plasticity index, it should be less than 20%. It is a bit more tolerant, whereas in the previous case the plasticity index was limited to 6%, and the soil should be compacted to at least 95% of the maximum Proctor density. And what are the design methods that we have? We can have for design purposes, the slopes are categorized into two different categories. Those slopes that are built on weak foundation soils, wherein the failure is happening within the foundation soil. So, we say that the embankment soil is strong, but then the foundation soil is weak. Or the other case could be construction of very steep slopes on a competent soil, on a very strong foundation soil, wherein the foundation soil itself is strong. And there are different methods for analyzing the steep slopes: planar wedge analysis, the slip circle passing through the toe, or the bilinear wedge analysis. We will see all these methods a bit later. Let us first look at how to construct the embankments on soft soils or soft clays. Usually the most of the problems are because of the construction on soft clays. What are the problems that we can encounter in the soft clays? They have very low bearing capacity. That means that the height of the embankment or the slope that you can construct is only limited, and you should expect very large settlements, and both total and differential, and then lateral flow of the soils that leads to the slip circle type failure. And in some cases the soil at the site may be so soft that we cannot even bring in our construction equipments, and the result of large lateral movements could be a slope failure like this. Originally the embankment was like this, and because of the lateral movement and because of the formation of the internal slip surface, the slope could collapse something like this. What are the different alternatives for construction in the soft clays? If the thickness of the soft clay is not very much, the easiest solution is replace the soil with a good quality soil. We just simply remove all the soft clay and then replace it with some good granular soil, or we can use a chemical or a thermal treatment of the foundation soil, so that we can increase the strength. That is the one simple form is just simply pumping in the concrete or the cement grout, deep mixing and the jet grouting, and then basal reinforcement, the basal mattress. Sometimes planar reinforcement may not be sufficient because of the height of the embankment. In such cases, we can provide a 3-dimensional type of mattress that could be filled with stone aggregates or some other very strong materials, so that we form a semi-rigid mat. Or we can use pre-consolidation with prefabricated vertical drains, or through the vacuum consolidation, or we can use our traditional stone columns or the encased stone columns. We can have piles with reinforced concrete slab, which is by far the most expensive ones, because we know that concrete is much more expensive than using just soil alone. Or we can go in for piles with the geosynthetic reinforced platform. These are called as piled embankments, and of late the last alternative has become very popular, because we do not need to wait for the pre-consolidation to be completed. You can go in and do the construction as the ground is being treated. This we will see in some other lecture. What are the shear strength properties that we can use for design of slopes? We should realize even before we design that these slopes, especially those resting on soft soils, we should expect that they will undergo very large deformations, and because of that we prefer to use, or it is recommended in the design codes, that we should use the shear strength properties corresponding to the constant volume state, or the constant volume strength parameters. Okay, and these happen at very large deformations, and the embankments are the slopes that are built on very strong soils. We can use the peak friction angle or the peak shear strength parameters. Well, just as we had very large number of load factors to consider in the case of retaining walls, even for the embankments we have a table that is given by the BS 8006 code that gives different material factors. For example, the load factors to consider for two different cases, one is the ultimate limit state and the other is the serviceability limit state. The load factor of 1.3 is recommended for embankment fill. Then other dead loads and line load, the point loads, the load factor of 1.2 is given. Then for the live loads, slightly higher, 1.3, and the serviceability limit state, as we have seen earlier, that relates to the regular service condition. So all these factors are 1, and then the soil material factors, especially when we use the 5 CV, because it is already factoring in lot of parameters like the loss of strength and then other parameters. We do not apply any other additional parameter on the 5 CV. So this factor is just simply 1, but then if we are using any C prime for effective stress analysis, we use a very high factor of safety, or the reduction factor 1.6, and if it is an undrained cohesive strength corresponding to large strains, we use a factor of 1, and even on the reinforcement strength we apply a lot of factors, and this should be consistent with the type of reinforcement and the design life and so on. And the factors of safety that we aim for sliding is 1.3, and against pullout is 1.3. is actually, if we combine this factor 1.3 against this live load and then the fill factor of 1.3, if you combine both of them, it works out to 1.3 times 1.3, that is nearly 1.7. So that is the that corresponds to the factor of safety of 1.7 in the working stress design methods. Well, in the case of very weak foundation soils, we go in for ground improvement, so that we can improve the soil properties to some reasonable level, wherein we can have economical solutions. Otherwise, the treatment could be so expensive, the construction could be so expensive because of the requirement of very large amount of reinforcement in the plane in the form of geogrids or the geocells and so on. Some of these ground improvement methods are very briefly. The stone column is one method. There are different types, the rammed stone columns and the vibrofloat stone columns that can be formed either by soil displacement or by soil replacement. This also we will see a bit later on in some other lecture. Here we see an example of an encased stone column, wherein we have a granular column, but that is placed inside the tube of geotextile or a geogrid, so that a combination of this granular material that is encased within the geosynthetic behaves like a very strong and stiff column. Okay, this we will see in some other lecture. And the particular photograph that you are seeing, this is the ground treatment that was given to the A380 factory in Hamburg, Germany. And another popular method that is traditionally used for ground improvement is the pre-consolidation, or we call it as accelerated consolidation. And in the early days, when this technique came into being, people used the sand drains or the sand columns, wherein we drill a hole, a bore hole, and then fill it with highly permeable material like sand or some aggregate. But with the advent of geosynthetics, we started using prefabricated vertical drains or PVDs, and the principle that is used in accelerated consolidation is we reduce the drainage path length, because we know that the time for consolidation T is related to the TV, that is the time factor that is related to degree of consolidation, and then the square of the drainage path length divided by CV. In this case, in this equation, the CV is a constant and the TV is also constant, because it is related to the degree of consolidation. Say for example, if you want a 90% consolidation, the TV we can get from the charts corresponding to 90% consolidation, and the only quantity that is variable is the drainage path length D. And if we do not have any sand drains, the water particle has to travel this much length to escape from the ground, whereas if we install these sand columns, the maximum length that a water particle has to travel is only this much, very small length, and because of that the time for consolidation reduces drastically, because the time is directly proportional to d square. And here is the schematic of the prefabricated vertical drain. It consists of a inner core and then an outer textile that acts like a filter, and here we see the installation of a prefabricated vertical drain. Actually it comes in narrow strips of about 100 mm wide and 2 to 3 millimeters thick, and this comes in a length of about 100 meters. And here we can see these PVDs installed at one site. Here you can see the ground treated with PVDs. Then on top of this, once we apply the surcharge load, either an embankment or our foundation, the soil quickly consolidates, and during the construction time itself we can achieve the all the settlements. The other popular method is the geosynthetic pile raft. Actually the pile raft is a very common foundation engineering treatment that we give for transferring heavy loads into soils with highly variable strata, or where the expected settlements are large. Here instead of the raft, what we do is we use a geosynthetic reinforcement, either a geocell or a planar reinforcement, to form a relatively stiff mat, and we use small piles with a pile cap, and invariably the piles that we use in the geosynthetic pile raft, they are plain concrete elements. They do not have any steel reinforcement, mainly because there is no bending. Here our slab that we construct does not have any bending stiffness, because it is all made up of flexible materials, and then the design itself is based on the arching theories that we will see later on, and this concept of the geosynthetic pile raft system has successfully been used at several places, and it is found to be very fast and also very economical compared to so many other alternatives. The other alternative is to use a very stiff mattress, that is by using a 3-dimensional geosynthetics like geocells, and this option is especially true when the thickness is thin compared to the base width of the embankment. And if this is the case, say let us say that we have a very strong foundation soil here, and at the top also we have very strong and stiff geocell. In this case the QU that we can expect is much more than 5.14 Cu, that is the normal Terzaghi's bearing capacity equation, that is the ultimate bearing capacity is about 5 times the undrained cohesive strength. But once we confine it like this, actually here is a schematic on how the bearing capacity increases because of the squeezing of the soil between two solid and rigid and rough plates, one surface made up of the geocell and the other surface made up of the rigid foundation. We have the slip surface is formed like this, and because of this our bearing capacity factor increases to almost 15 to 16. And here on the left hand side you see an example of open geocell matrices being fabricated at the site, which will be later filled with stones or boulders or aggregates to form this stiff geocell matrix. This also the design and construction aspects we will see in some other lecture. Another very popular method is the use of vacuum pressure for accelerated consolidation. Here what we do is we seal the soil to be treated completely by using geomembranes or some other techniques, by digging in trenches and filling with some bentonite and or polymer mixed bentonite slurry, and so that the entire volume of soil that is to be treated is sealed, and we apply vacuum, and once we apply the vacuum, the atmospheric pressure, that is actually basically we are removing the atmospheric pressure from inside this volume of soil that needs to be treated, and the atmospheric pressure starts acting. And the main advantage here is we achieve the increase in the effective stress to drive our consolidation without any increase in the total stress. That means that we do not need to bring in the soil and dump it at the place to achieve the consolidation, and then the increase in the effective stress is constant with the depth. That is the major difference between this method of treatment and the other methods, because in the normal the conventional surcharge method we need to bring in the soil and put it in, and because of that the stresses that are generated, they are anisotropic. The stress is more in the vertical direction compared to the lateral directions, and because of that we generate shear stresses, whereas here the vacuum being an isotropic stress, there is no generation of shear stresses. And on the right hand side bottom you see a small example of a laboratory test being performed to achieve the vacuum consolidation. And now let us come back to the to the design of basal reinforcement, and in many cases the basal reinforcement is also used as a construction expedient, because some places the soil may be so soft that we cannot even bring in our construction equipments for doing the minimal construction work. In such cases, what we do is we provide a very strong and stiff basal reinforcement along with the sufficiently thick granular soil, so that we can freely bring in our construction equipment and start the construction process. And we can also provide it to increase the factor of safety of the embankment. And the design methods, they are very similar to the standard design methods that we normally use in the soil mechanics courses. And let us first look at the basal reinforcement design for phi equal to 0, or the undrained analysis or the total stress analysis that we normally study in the soil mechanics courses. And because the soil is purely cohesive, we can assume a circular slip surface like this, and for any given slip surface like this, and we can calculate the weight of this soil wedge that is within this wedge, that is the W, that is trying to destabilize, and that destabilizing moment. So, if you draw the slip surface with respect to a center here and a radius, this volume we can easily calculate, and that the weight of the soil is just simply the volume of the soil multiplied by corresponding unit weight and multiplied by this x bar, that is the distance of the center of gravity of this area from this center point, that is the disturbing moment. And then the resisting moment is because of the cohesive force that is developed along the slip surface length. So, it is just simply Cu multiplied by length of the arc La, and that is the resistance force, and this multiplied by this lever arm or the radius r, that gives us the resisting moment. And so, our factor of safety against the failure is the resisting moment divided by the upsetting moment. In this case, our resisting moment is because of the cohesion that is developed along the length of this slip surface, Cu times La times r, and our La is nothing but the length of this slip surface, that is equal to radius times this theta in radians. And suppose this factor of safety is not adequate for our construction purposes, we can add in some basal reinforcement, and that can increase our factor of safety. And the typical factors of safety that we aim for are about 1.3 to 1.5, depending on the importance of the structure that we are building. And after providing this basal reinforcement, the factor of safety increases because of this additional moment, the stabilizing moment that we get, and the additional stabilizing moment is added on to the stabilizing moment because of the soil resistance. That entire quantity divided by W times x bar is our factor of safety of the reinforced slope. And invariably, as we know, the slope stability analysis is a very tedious process. We need to consider different slip circle center points and then the radius, so that we identify the most critical slip circle. And it is not necessary that the critical slip circle for the unreinforced soil is the same as that for the case with the basal reinforcement. And so, we tend to use some computer programs that can automatically do all these design calculations. And there are two cases that we can consider, because sometimes the basal reinforcement could be provided in the form of steel strips or welded wire meshes, and in such cases where the reinforcement is very stiff, we can assume that the reinforcement remains horizontal, whereas if you provide a flexible type reinforcement like the geosynthetic or a geotextile, it is possible that at the point of the contact with the slip surface, there will be a kink formed within the geosynthetic, and at this point we can assume that the reinforcement force is acting along the slip surface or tangent to the slip surface, and this we call this type of reinforcement as a flexible reinforcement. And because the reinforcement force is acting tangent to the slip surface, the lever arm for this is the radius r, whereas for the previous case where the reinforcement force is acting horizontally, the lever arm is the vertical height from the level of the reinforcement to the center point of the rotation. And depending on the type of reinforcement, we can calculate the stabilizing moment as the reinforcement force provided times lever arm, and this reinforcement force is actually, as we have done in the case of retaining walls, it is the minimum of the tensile strength or the pullout resistance, and so this and we can actually by looking at this equation that the moment due to the reinforcement is just simply the T times the T is the reinforcement force multiplied by the lever arm, and by from this equation is actually here the first term that we have, the Cu LA r by W x bar, is nothing but the factor of safety of the unreinforced slope, and by using that relation we can calculate the magnitude of the reinforcement force that needs to be provided as in the form of basal reinforcement is the difference between the factor of safety of the reinforced slope minus the factor of safety of the unreinforced slope multiplied by W x bar by lever arm, and so we should provide this much of basal reinforcement that develops this much of force, and sometimes we may not be able to provide it in one single layer. We may provide multiple layers, say some 2 or 3 layers to increase the to provide sufficient force. And as I mentioned before, the reinforcement force that we consider is the lower of either the tensile strength or the pullout resistance. And when we do these calculations, we should also consider the case of the sliding of the entire reinforcement mass or the entire soil mass like this. So, let us say that we have built a slope with some basal reinforcement based on our slip circle design, and we should also make sure that the extreme case wherein the lateral forces that are acting inside the embankment should not push out the entire slope like this, and the length that we have, it should be sufficient to resist the lateral sliding because of this the different forces, the triangular distribution of forces because of the self weight, and this rectangular distribution of forces because of the uniform surcharge. And in these calculations we see that the shear resistance is developed only on one side, on one surface, and this lateral force P that is trying to push our slope away from the rest of the soil mass is 1/2 Ka gamma h square plus Ka times QH, which is the same as earlier, except that the Ka here is different because our the Rankine's Ka is applicable for vertical retaining walls, but here our slope is not vertical, but it is inclined at an angle of beta, and our Ka is given as sine of beta minus phi by square root of sine beta plus sine phi times square root of sine beta, the entire thing to the square. And if you substitute a beta of 90 degrees, that is corresponding to vertical retaining wall, this comes to 1 minus sine phi by 1 plus sine phi, and invariably when beta is less than 90 degrees, this Ka is much less than what we had earlier. And we should also consider the possibility of the provided reinforcement pulling out of the soil, and let us say that the length of the reinforcement beyond this this position is Le, and we should make sure that this length Le is sufficient to generate the pull-out resistance against this lateral force with some sufficient factor of safety. And even in the earlier case, when we do this slip circle analysis, the length of the reinforcement that is generating the pull-out resistance is only the length of the reinforcement beyond the rupture surface, and the quantity of reinforcement is not only a function of the rotational stability, but also a function of the lateral sliding forces and pull-out forces. Previous analysis is only valid for phi equal to 0 type of soils or undrained behavior of the clays, but sometimes the soil may have both cohesion and a friction angle, and in that case our strength varies with the depth of the soil, and we can use our conventional slices method, and this is the ordinary method of slices or the Felenius method, or we can also use the Bishop's method of slices, wherein we do not consider the entire soil surface as one single mass, but we divide this into certain number of slices, usually at least about 6 to 10, and the more number of slices we have, the more accurate is our result. And we look at the equilibrium of each of these slices like this. Let us say that Wi is the weight of the soil within this slice, ith slice, and because of this there is a normal force N, and then a tangential force T, that is the sliding force, and N is nothing but Wi times cosine alpha I, where alpha I is the inclination of this base of the ith slope, ith slice, and the Ti is Wi times sine alpha I. And for a general case where we have pore water, there could be some pore pressure U because of the seepage or some other factors, and so we can write our factor of safety against slip circle failure in the same manner like earlier, by taking moments about this point, the C prime, that is the effective cohesive strength, multiplied by the La, that is the length of the slip surface, that is the r times theta, times r, that is radius of the slip circle, plus the moment that is generated because of this resistance by this N, the normal force, that is tan phi times Wi cosine alpha, that is the normal force, minus Ui, that is the pore pressure, multiplied by the base length Li, that is our resistance force, and that multiplied by r, the radius, will give us the resistance force, and then together with this we add some the resistance that we get because of this reinforcement layers, and if we provide multiple layers, we do a summation, the T multiplied by either the vertical height yi or the radius, depending on the type of reinforcement that we provide, either rigid reinforcement or a flexible reinforcement. This entire thing divided by the upsetting moment, that is the Wi sin alpha I multiplied by r, and so this this will give us the factor of safety of the reinforced slope, and as I mentioned earlier, the target factor of safety is about 1.3 to 1.5, and we need to do some trial and error analysis and find out the quantity of reinforcement that we need to provide. Here the analysis is a trial and error, because the resisting moment also depends on where you place the reinforcement. If you place the reinforcement at a slightly lower depth than the base of this embankment, you get a higher resisting moment. And the more accurate way of doing the design calculations is through the Bishop's equation. The Bishop's equation is given like this, which is very similar to the earlier one, except that we have the factor of safety on both left hand side and the right hand side. Actually it is an implicit equation. We need to do some trial and error, like we first assume some factor of safety based on the Fellenius analysis, and then substitute that on the right hand side, and the factor of safety that we get from the first analysis is once again substituted back, and we do these trials until both left hand side and the right hand side are equal. Okay, whatever is assumed is equal to the calculated value, and here all these parameters are the same as earlier, except our B is the horizontal width of this slice, and RU is the pore pressure parameter, Bishop's pore pressure parameter. Typically this is about, it depends on the type of soil and then the type of drainage conditions and so on. It could be anywhere from 0 to about 0.4 to 0.5, and our Fs is the factor of safety, Fsu is the factor of safety of the unreinforced slope, and then Fsr is the factor of safety of the reinforced slope, and by using these equations we can come out with the quantity of reinforcement, and all these calculations, they are done by using some computer programs, and here you see an example of a computer program result, and this computer program you will get it as part of this course, and here you see the factor of safety of an unreinforced slope and with some tension crack, especially when you have a clay soil, we should expect the formation of tension crack. The tension crack height, we know that this height is 2c by gamma square root Ka, and in this particular case the factor of safety is only 0.66. So, we need to bring it up to say about 1.3 or 1.4 by doing some trials and by putting in some reinforcement of different strengths or different locations. So, we will see some numerical examples to illustrate these procedures a bit later on, and now let us go on to the construction of embankments on competent foundation soils. The case in point could be very something like this. We have a foundation soil that is very strong, and but we want to construct a very steep slope using the existing soil. Let us say that the given soil at a site is stable at this shallow angle, and but then if we use a very shallow slope, the required space is very large, and if we want to increase the slope angle, we cannot do it, because the frictional strength and the cohesive strength, they are not high enough to support a steep angle. And in that case, what we do is we can provide some layers of reinforcement like this, and we can either say that we get extra space for our road, or if you if your line of property is only up to here, from here we can construct a very steep slope, and then finish our construction without acquiring any land. And here we see the shallow unreinforced slope here, and then a very steep reinforced slope, and the quantity of the reinforcement that we provide here is the variable that that needs to be decided. And there are several methods that we can use, that is the planar slip surface method, or the circular slip surface method, or bilinear wedge method of analysis, and so on. And that I think we will take up in some other lecture. Okay. Thank you very much.